Hello everyone, welcome back to my YouTube channel. I am Manoj K.S. from Sri Venkateswara College of Engineering, Bangalore. My USN is 1VE23IS027. I am pursuing my fourth semester of BE from the Department of Information Science and Engineering. The subject for today's video is Analysis and Design of Algorithms. And the topic for today's video is Analysis of Algorithm Efficiency. Let's see the introduction. Decoding Algorithm Efficiency. Algorithm efficiency is a fundamental concept in computer science that evaluates how effectively algorithms perform in terms of resource usage. Understanding this concept allows developers to design solutions that run faster and consume fewer resources, crucial in today's data-driven world. This presentation dives into the critical aspects of algorithm efficiency, including time and space complexity, asymptotic analysis, and practical implications in real-world applications. What is algorithm efficiency? Definition: algorithm efficiency refers to the amount of resources an algorithm consumes. These resources typically include processing time and memory. Space complexity represents the number of auxiliary storage an algorithm requires, which grows with input size. Time complexity: it measures the execution time related to the input size, highlighting how performance scales. Key metrics: it includes CPU cycles, memory allocation, and disk input or output operations, which affect overall performance. Asymptotic notations. Big O notation. Overview: Big O notation expresses the upper bound of an algorithm's running time or space usage as input size grows. It focuses on the dominant term, ignoring constant factors and lower order terms for simplicity. The common classes are O of 1, which is constant time; O of log n, which is logarithmic; O of n is linear; O of n log n, logarithmic linear; O of n square, quadratic equation; O of 2 power n, exponential; O of n factorial is a function of factorial. For example, O of n square plus n simplifies to O of n square because n square dominates as n grows. Time complexity examples: O of 1. Accessing an element by index in an array takes constant time. O of log n. Binary search efficiently finds element in sorted data with logarithmic time. O of n. Linear search checks each element, taking time proportional to input size. O of n log n. Algorithms like merge sort achieve efficient sorting in log linear time on average. O of n square, which is bubble sort and insertion sort, have quadratic time complexity in worst cases. Space complexity examples: O of 1. Constant space. Iterative algorithms that use a fixed amount of extra memory regardless of input size. O of n. Linear space. Algorithms that require extra memory proportional to input, like making a copy of data. O of n square is quadratic space. Storing adjacency matrices or 2D arrays consumes memory going with the square of input size. Recursive call stack. Recursive algorithms often have O of n space complexity due to the depth of the call stack. Best, average, and worst case analysis. Best case: minimum required resources. Example: finding an element at the start of the list. Average case: expected resource usage, often complex to calculate, averages performance over all inputs. Worst case is the maximum resource usage guarantees, important for understanding upper bounds. Example is quicksort. Average case: O of n log n. Worst case: O of n square when pivots selections are poor. Practical implications or real-world scenarios. Sorting large datasets. Choosing between quicksort and mergesort impacts speed and memory use. Mergesort guarantees O of n log n consistently, while quicksort is often faster but with a potential worst case. Searching databases. Indexing structures enable O of log n lookup times, optimizing queries in massive datasets like those powering search engines. Graph algorithms. Complexity influences social network analysis. Efficient algorithms enable scalable computations on big graphs representing billions of connections. Amortized analysis explained. Definition: amortized analysis averages the cost of an operation over a sequence, smoothing expensive occasional operations. For example, dynamic array resizing in Java's ArrayList occasionally resizes to O of n, but the amortized cost per insertion is O of 1. Its importance is this analysis is essential when evaluating data structures with infrequent costly operations ensuring efficient average performance. Thank you for watching the video.